Hello and welcome. This is going to be an introduction to tornadoes. And tornadoes as you're used to them, but also families of tornadoes you've probably not thought of before. We're going to classify them a bit more discreetly than just a tornado. We're going to deal with the theory of their formation, something called tornadogenesis, and we're going to model that in real life. And to model it, we need to understand a little bit about what we're looking at. All right, so the National Weather Service defines a tornado as a violently here means strongly rotating, probably in the neighborhood of 100-mile-an-hour winds or more in general, rotating column of air touching the ground, so the rotation has to be at ground level, attached to the base of a thunderstorm. And this definition is fine for what it is, although it is too broad for us. We need to classify them into smaller categories because really tornadoes do take on several different identifiable families here, and they have different impacts. For instance, the kind of tornado here in this video is significantly more violent than related thunderstorm tornadoes that can happen in our area called landspouts or Gustnadoes. And so we need to understand what makes tornadoes different and what would be the ingredients needed to get these strongest tornadoes. No matter what kind of tornado you're dealing with, it's going to be associated with a cloud. If there's not a cloud, you can't have a tornado. So again, I want you to hear that. If there's no cloud above the vortex, you are not dealing with a tornado, period. Okay. The storms are going to rotate cyclonically, at least in general. There are anticyclonic tornadoes, although they're quite rare. And because it is cyclonic, at the bottom you'll see it is an area of low pressure. So in the northern hemisphere, this means they're going to rotate counterclockwise. In the southern hemisphere, okay, whatever. But we're here. This cyclonic rotation low pressure does mirror a low pressure system on the scale of like a hurricane or mid-latitude cyclone, but they're not exactly the same. The pressure drop is significantly stronger within a tornado. The pressure in the middle of a tornado is significantly lower than the center of a low, for instance. Tornadoes tend to be small, as you know. They tend to be significantly less than a mile wide, although they can, in occasions, be wider. And they're transient. They don't last more than a few minutes for the most part, although occasionally, again, they can last over an hour. And they tend to move in addition to being short-lived. So a tornado is a very short-lived event at any given point. And wherever they form is located in wind shear. And that's a term we haven't actually talked about yet. Wind shear means the wind is changing with height, generally in respect to speed and direction. Something we will deal with a little bit today and significantly more in an upcoming lecture. So again, we have these things under a cloud. If there's no cloud, no tornado. They rotate around low pressure, and the result of that is an area which is generally quite tight, kind of like a figure skater pulling her arms in. This is not going to be a wide feature. And that's because of wind shear. Again, that change of variable with respect to height. So here are two pictures of vortexes, but only one can be a tornado. Which one? Again, that's because the picture on the right doesn't attach to a cloud. You must have a cloud base above the vortex. So even though the thing on the left doesn't really look like a tornado to your eyes, it must be because it's associated with a parent cloud. Again, why couldn't this be the result of a tornado? We're looking at damage here. You can see there's a lot of trees that have been knocked down. Obviously, the winds here were excessive, probably well over 100 miles an hour in this moment. But why wasn't this a tornado? I want to point out that tornadoes can really have a small of a radius as needed. They don't have to last a very long time at all. They don't have to move at all to be considered a tornado. As long as you have a rotating updraft in contact with the ground, we're going to call it a tornado. And a lot of tornadoes fit this category of 30 seconds to a minute on the ground for a mile or something, a couple 100 feet wide, and that's that. A lot of tornadoes, most tornadoes even, look a lot like this picture. Although this one's quite tall, one might be a little more squat. I want to point out that tornadoes exist as soon as dust is rotating on the ground or any other debris. Sometimes in an urban environment, you might see leaves and shingles or something like that. And both of these count as tornadoes, albeit two different kinds here. So these are tornadoes despite not looking like tornadoes. They are localized, rotating, violent columns of air. The one on the right is more likely to do damage than the one on the left, both because of its location, but also its shape. The one on the right is associated with a very weak funnel at the top. If you notice, the one on the left doesn't show any real attachment to the cloud, but because it's located underneath the cloud, the only way it can be there is because of the cloud. So both of these count as tornadoes, even though there is no direct cloud contact. Now, Tornadoes often do form condensation, that is clouds that mark the entire vortex, as seen here in this rather photogenic tornado taken from the south of the storm. But that's not required for the storm to do damage. As a matter of fact, this tornado, being out in the middle of the field, almost certainly did no damage. That being said, the condensation funnel connecting the cloud to the ground is not required for the definition of a tornado. Any dust cloud underneath it that is rotating and localized is going to count. Let's classify tornadoes. The most common kind of tornado that you're thinking of, the big dog here, the most dangerous, are called supercellular tornadoes. This is a particularly violent tornado here, at least by appearance. And so these are the kind of tornadoes that you're used to thinking about, the ones that movies get made of, they're the ones that you get warnings for. These are by far the most important tornadoes. Supercellular tornadoes are violent in terms of their wind speeds. They can exceed 300 miles an hour by Fujita's measurements, or 200 in modern estimates. Realistically, the answer on the strongest tornadoes is probably between the two. The tornadoes that are supercellular tend to last longer and be wider. And so because they last longer, are bigger and faster, they tend to do the most damage. So these are the ones that we're most interested in providing warning for. And their parent storm is what's called a supercell. Again, a term we haven't actually discussed in this class at length yet, but we're going to call this a severe thunderstorm. So associate this thunderstorm with a rotating, strong, robust thunderstorm that's already there. Things that are likely happening are lightning and hail and damaging winds are probably already in place by the time the tornado forms. In other words, the storm doesn't just pop out of anywhere. It generally forms over the course of maybe an hour before a tornado is particularly likely, and all but the most explosive days. And so these are going to be our storms, and they're associated with these supercells. Supercellular tornadoes are much larger than just a tornado on the ground. I've circled an image here, and this is one of the most characteristic parts of a supercellular tornado on the backside of the storm, something called the RFD. Again, a term we'll take a look later. But the interaction of the cloud above the tornado and something called a mesocyclone is what's making the tornado underneath it more likely to be strong and long-lived. So because this whole storm is kind of working to produce a rotating updraft, the tornadoes have higher impacts. Now, you'll notice this has a big shape all the way around the tornado, and we'll talk a lot about what that shape is and why it's there. But I just want you to notice this tornado isn't just coming out of a flat cloud. Already the cloud looks very strange, looks very characteristic to these things. Even without a tornado, that part of the cloud tends to rotate quite clearly, and we will talk again at length about why this is and how it happens. But I want you to notice, like, the ingredients for a supercellular tornado involve, at least in part, a very special kind of rare thunderstorm. Maybe 1 in 100 thunderstorms have this kind of shape and structure and ability. So we're dealing with a relatively rare situation to start with. And then within those 1 in 100 storms, even fewer produce tornadoes, and even fewer in there are violent tornadoes. So they're still incredibly rare, but they do share this supercellular characteristic. Everything else is going to be non-supercellular by definition. So this is a waterspout off the coast of Florida, and you can see, of course, that this is not associated with that same shape. It's coming straight out of what looks like a relatively normal cloud. It's not nearly the same visually. And these NSTs, as they're generally referred to, they really tend to be weaker storms. The most common one, the one that most people will be familiar with, are waterspouts, which seem to be just defined poorly as a tornado over water. That's not exactly true. You can take a look at this picture here and get a pretty clear idea this is not the same as a supercellular tornado. Not for the least of which is it doesn't come out of a rotating parent thunderstorm. It's just coming out of a thunderstorm. It's not got that whole structure supporting the tornado, right? It's still gorgeous. It's still absolutely dangerous if you're on a boat, but it's not a tornado in the way a supercellular tornado is. We're still going to classify it as a tornado, but waterspouts are just vortexes over water. And because of that, and because they're not associated with a supercell, they're generally significantly weaker. Now, that is an asterisk term. You can technically have a supercellular waterspout because our waterspout definition just includes tornadoes that have crossed over water. That being said, unless you have something like a giant lake, in general, we're not going to make that distinction. The tornado is going to be on the ground before and after the lake, and it's just part of the tornado's path. We're never going to stop calling it a tornado in practice, right? We're really talking about this kind of vortex that connects up to a flat cloud. And I think you can see the difference here if you compare what we said was a supercellular tornado on the right and on the left a waterspout. You can see how the whole cloud is kind of lowered down and rotating around the supercellular tornado versus the waterspout on the left where it's just a vortex. Because of that, it's a lot easier to get these vortexes. Clouds are common, and the feature that's forming here is not exactly related to the way supercells form, so you can get families of waterspouts pretty commonly. That is, a lot of waterspouts in the same spot. And this is a good way of proving that they're non-supercellular. This would be absolutely impossible in a supercellular tornado because, again, the whole storm is kind of working around that vortex. Here, these are very localized effects that seem to be related to just right where that vortex is. Otherwise, you can't form a lot of them. And so this makes them easier to do the math on and physically make. And so waterspouts are a little easier to understand than supercellular tornadoes. That being said, you don't need the ocean to do it. This is a picture that seems kind of strange. Maybe this is like a bay or whatever, but you can see land across the way, but that's even not what it is here. This is a waterspout. You can see the flat cloud above it. Just kind of looks like a standard summer rainstorm and a clear vortex. And this actually formed in Lake Manawa, just outside of Omaha, a couple years ago. And here's a video of it from a plane making an approach to Epley. And you can see again how flat the clouds are, how non-severe looking the clouds are. It just looks like a normal cloudy day in the Midwest. And here's this waterspout formed over a lake in the middle of Iowa, or the edge of Iowa. That's I-80. We just flew over there, right? So it's kind of crazy to see this. This was a super neat event, and I want to point out incredibly rare. The idea that you can see this from multiple angles is just incredibly lucky. But this isn't technically a tornado, and the dynamics of this mean that it's not really going to move on shore and do tornado-y damage, right? It's going to be a waterspout, and why that waterspout is there is related to the lake and the cloud above it, and less to a parent weather system. So this is a relatively rare thing to see. As a matter of fact, I don't know if I've seen another inland waterspout so well defined. We also have these things called landspouts. And they're the same thing as a waterspout, but they form over land, which is weird, right? They're going to have a few things that are different. So they're wider at their base than the top. That's really characteristic to them. Generally, the base tends to be very dusty. In general, they're weak, but they can be damaging to a pretty significant degree. Like, we're talking leveling houses level of significant. And again, you can see on the right here, this landspout doesn't have that characteristic supercellular structure. It tends to be this kind of higher-based little tubular tornado attached to a flat cloud. You can see it here kind of in a more typical, less photogenic example. And you can really see this doesn't look like a tornado-producing situation. It just looks like a rain cloud, and all of a sudden there's a vortex in the middle of it. Again, that cloud base not having that whole rotating structure above it is really distinct. They almost always form at the beginning of a storm, right? When the updraft is just forming. Look at these clouds. These are not what you think being rain clouds or thunder clouds, and yet here it is producing a vortex that goes, a mile plus into the sky. That's crazy. And that's because these clouds are just starting to bust through the cap, and they've got a lot of vertical motion in them, and it allows them to pull up existing vortex tubes. Something we're going to talk at length about. So landspouts tend to form in this time. And again, this is obviously not a strong situation in most parts. It's just a vortex. But it's also different than a dust devil, where it's just a heat specifically caused cloud. This is still associated with a cloud, and as a result can be strong enough to do damage. If you get close to a landspout, they tend to have this characteristic wide, kind of swirling, dusty look. This is kind of the most famous picture from a guy by the name of Jim Reed. And you can really see how those clouds are towering in the background, right? They've just broken through the cap, they're going up, and that updraft is stretching this vortex to it. You can see that wider base, that dusty base we talked about, that's better defined. It kind of gets thinner and more opaque as you get away from it. Okay, that's going to be our landspout. And if you actually go back to a waterspout that does look different than a waterspout, which looks more like a traditional tornado, and that comes down to the reason why these storms are forming. There are small distinctions between landspouts and waterspouts. For this class, it's just that a landspout is over land. I also want to point out that these tend to form on a surface shear boundary. So surface shear boundary just means an area of converging winds, where winds are coming from different directions and hitting into each other. Here's a picture taken from like a local news channel, and you can see where they've drawn it in really well, but this is actually quite true. You get these little puffy high clouds, and if they form right over a convergent boundary, that's when you get landspouts. They're extremely hard to predict. They tend to be very short-lived, and as I said, particularly weak, but when they form, they can be photogenic, that is, they can be pretty, right, easy to take pictures of. They can be, if you're in the wrong spot, dangerous. And absolutely, without question, they can be concerning if you look out and you see them, and all of a sudden, you see this thing coming towards you. You think Wizard of Oz, Dorothy's coming, right? But no, actually, generally speaking, these tend to be weaker. But because they're associated with a cloud, again, they can be more significant. Before we go on to Gustnadoes, actually, I do want to point out that landspouts occasionally can form families, just like waterspouts. And again, the parallels between landspouts and waterspouts was something that was first noted in 1985 by a guy named Bluestein. Okay, so it's a relatively recent thing to start classifying them this way. That being said, again, these are very clearly not tornadoes in the way we're used to, and that's why we do them. Probably the least tornadic looking thing is something called a gustnado, which is an area of rotation in a dominantly outflow area. Generally, it's associated with this big long line of thunderstorms instead of a cell. We'll talk about that later. And another reason I even bring them up is they can do significant damage occasionally. Now, again, for the most part, these are just a dust cloud that's spinning. This is a gustnado. I've driven through several of these. They have strong winds in them, but they're not crazy, maybe 80 to 100 miles an hour, and they're dusty. They don't really fit the tornado the way we're used to it. Except sometimes they do. Right? Here's a gustnado in its beginning form, and again, calling this a tornado seems to be a stretch, but if we're going to define a tornado as a rotating column of air in contact with the ground under a parent thunderstorm, well, there is rotation within that front updraft. It's moving relatively quickly, and it's in contact with a thunderstorm. So it checks all the boxes, but it doesn't feel quite right. Now, normally these are on the front of the thunderstorm, but occasionally they can form on the back. Here's a gustnado I observed in Oxford, Nebraska in 2011. You can see on the left over the road is the wall cloud. That would be where the normal supercellular tornado forms. And I put a box to the right around a gustnado. You can see it's not associated in any way with that whole supercellular structure. And yet here it is on the ground. This actually did somewhat significant damage. I believe it was ranked in F2, something we'll talk more about later on. And so as things go, you can get these kind of rotating, outflowy, local things called gustnados. And for us, if it looks like a big cloud of dust, it's a gustnado. But these tubular vortexes, those are going to be our supercellular tornadoes or our landspout, waterspout. So what kind of vortex is this? I do think it's particularly neat. You can see the pattern of this cloud interacting with the water, and that same shape would be located around most vortexes. And that's something we're going to look for in our modeling physically in a minute, is, can we get that shape? Okay, again, what kind of tornado is this? I want you to notice, again, that the cloud around the vortex is all moving violently. This whole thing is associated with that tornado. If you look really carefully, the area to the, in this picture, west and south, that would be behind the tornado and a little bit to the left, is lighter. And again, that's that notch we're going to talk about later on. This is a strong tornado in this picture. What kind of tornado is this? Because we're going to model a landspout, that is, when we go upstairs and work with the tornado machine, we're going to model a landspout. I do want to show you some landspouts as more than just GIFs or pictures. So here are a couple videos. We're not going to watch them all. These are out of Mexico of landspouts. And I want to show you some things in these. I'm going to narrate them. Again, I want you to notice how laminar, that is smooth, the vortex looks compared to tornado. It's a much more gentle looking phenomena. Again, here's our family of landspouts. We can see there are 3 of them there. And you can see this doesn't quite look as angry as a supercellular tornado. It's kind of tornadoes you're used to. But it also looks scary. If this is coming towards you, you freak out. As this person I'm sure did. I want you to notice again how they're more defined at the ground than when you go up. So down here it's dusty and very tornado looking. And as the person starts to look up, you might see the vortex. Now again, I've said that like if this is your warehouse here, you're going to care that this thing is there, right? This is going to take you a while to undo this. But again, the same way, it's not just like leveling this structure. It's doing moderate damage here. Let's look for that more defined base here in a second. There we are. You can see these landspouts, again, as a family, which is kind of cool. Down at the ground, there seems there are 5 there. This one's pretty cleanly all the way to the cloud, although again, you can see that flat cloud top as we're kind of associating these with. And the fact that the storm is more elevated is also kind of indicative of a landspout. These don't generally form real close to the ground like a tornado does. Here's a good example of it being wider at the bottom and cleaner at the bottom. As you go up the vortex, you can see it gets less and less dusty and narrower, and that's really characteristic to these landspout tornadoes compared to anything else. So this would be kind of your textbook landspout picture here, and that's quite a strong landspout. That would be concerning for certain. Really quickly, let's talk about how they form. So wind shear means a change with something with respect to height, right? So here we're changing speed and speed only with respect to height. As we go farther off the ground, the wind is going faster. Super common situation because there's trees and buildings and hills up near the ground. It acts as friction and wind slows down near the ground. This is even, I would say, the dominantly normal way the atmosphere looks. If we take that wind and we put like a paddle wheel in it, you can see that the force is not going to be applied equally. What's going to happen to this? Is it going to spin clockwise or counterclockwise? So you're going to get this rolling motion with respect to height as the result of your wind shear, right? Think of it as like a pencil between your hands. If you take the top hand and the bottom hand, you move the top hand faster to the bottom, it's got to roll that pencil along, right? So we're going to make a rotating tube of air along the ground, something like this, right? And these tubes of rotation exist all the time. They're not particularly special, but if you can get a particularly strong one and make it stick at one spot, say at a convergent boundary, as we've talked about, and you've got a cap break situation going on, that's when you're going to get landspouts to form. What's going to happen is, now you get a bigger thunderstorm that starts to form, and a thunderstorm is an area of what? Rising or sinking air. And so we get this strong rising motion under the cloud, right? And that's going to come near our vortex tube. I want to be clear that the rising motion within a cloud is a lot stronger than you think. This is not about to make a tornado, despite what it looks like. It just looks scary, but these are particularly benign looking. This is just a strong thunderstorm pouring air towards itself. It's a time lapse. You can see how fast the clouds change. You can see this thing really sucking the air up from the ground, trying to pull air into itself. And then the storm passes. Well, if you get that strong localized pulling of air up, and it goes across a strong localized rotating area, right? Like these two situations, and they cross, then we're going to get to this situation, which is what a meteorologist calls cyclostrophic balance. What part of this word looks familiar to us? So this is the cyclone balance of wind, and this is where things get elegant. All of this modeling, we can really get to a landspout with just 2 variables. How hard is it spinning, and how hard is it being pulled towards the middle? It's no different, really, than like a toy airplane on a string or a sling, right? All we're doing is we're keeping things in balance from being flung away, right, or sucked in. And all we need to do then is provide both a pressure gradient, that is a lower local pressure, as well as a tangential force, that is a wind that blows around that low pressure, and we should get cyclostrophic balance to occur. This is a pretty common situation. This isn't different than the way the vortex forms in a bathtub. This isn't all that different than the way a dust devil forms, which isn't a tornado at all. But this is the basic mathematical model for what's going on. Now, we could do the calculus here. It's not particularly difficult, but we're not going to. And so what we're going to do is we're going to say that all of a sudden we have this pull that's balancing out this existing tube, and we're going to suck that tube up vertically. And as we reorient it from that horizontal to that vertical, that's when you get landspout formation. Now, in a minute, you're going to go upstairs, or maybe you already have been upstairs, depending exactly where you are in this, and you're going to see this in practice. We're going to provide a rotating force and a lifting force, and we're going to make them interact in a balanced way, and we'll get a stable vortex out of it. In truth, even in a supercellular tornado, right, the big king of tornadoes, this process is still going on to large part. You've got a violent updraft, and you have existing spin in the air, which is being kind of capitalized on by that updraft. Now, once the storm actually gets going and the tornado is formed, it can kind of create its own weather for a while too. It's a little more complicated. The math isn't quite as neat as just the cyclostrophic balance anymore. Besides the point. The point is, when you go up and we work with the model, if you've already seen the model, this is real. That's an actual vortex formed the same way under the same basic conditions that a landspout happens. And to me, that's really cool. Again, the world's a really complicated thing, and this shouldn't be. All we're doing is we're taking rotating air and we're tilting it vertically, and that results in these families of landspouts. A couple questions here at the end to help out and just give you some points. And that will take us into radar identification of rotating thunderstorms.